20%. But a lot of the regions of the world, including the United States, still very uncertain. So that's why we really need to continue to do research, and we need to do research on the local scales to try and really capture what's happening in the water cycle. So summarizing my global picture, we have increased surface evaporation, which is on the order of 2% per degree C globally. This is from the climate models. We also have an increase in precipitation because there's more moisture in the atmosphere due to the increase. And in order to balance on the annual basis, we have the similar increase in precipitation, 2% per degree Celsius. So these two terms balance to zero over the annual cycle, over a year, and the units are about 486 on 10 to the cubed kilometers per year. However, we have differences in land and ocean. Over land, we have more precipitation than evaporation, which leads to runoff. And as I showed you over the ocean, we have more evaporation than precipitation, so the ocean is a net source of moisture. Locally, however, these changes can vary a lot depending on the dominant precipitation processes, rain, snow, drizzle, and evaporation. It turns out, by the end of the talk, I hope I can convince you that evaporation is just as important as precipitation. Because in many parts of the world, the evaporation of water is on the same order as the production of precipitation. So now let's look at the different components of the cycle. This is now from the CMIP RCP 4.5, which is similar to the A1B scenario. And I'm going to look at precip, soil moisture, runoff, and evaporation. Here you can see the units. This is the change over the 21st century from the 20th century. And this is now with 14 models ensemble. Again, if we can look at Thailand, we can see, again, it's predicting, as I mentioned earlier, increases in precipitation on the order of 10 to 15%. Soil moisture is increasing maybe, or about 3%. Runoff is light blue, plus 20%. So increased runoff. So this could be an indication of more flooding, and I think other people have indicated the same thing. And then evaporation, also more evaporation. So we're getting a warmer climate and getting warmer increased evaporation. Over the whole globe, if you average this over the whole globe, we get a precip increase of 3%, evaporation increase of 4%, and a runoff increase of plus 6%. So the terrestrial water cycle seems to be accelerating in the future world. Now let's look at a couple of different locations around the world. I gave this talk about a month ago in Israel at Tel Aviv University. So if you look at Israel, the precipitation is actually decreasing by minus 10%. Soil moisture is decreasing by 3%. Evaporation is increasing. They have a runoff change of minus 24%. So exactly the opposite of what is predicted for Thailand. This is what I just mentioned for Thailand. You have an increase in precipitation. So if you go back and forth here, you can see precipitation is obviously one of the keys. Whether we have a positive increment or a negative increment will oftentimes drive the runoff. The evaporation term is actually quite similar. Now these are global models that I'm talking about. So obviously we need to look at the regional scale because there are very many local impacts of the land and sea on orographic terrain. I'll talk a little bit about that. So the approach that I'm going to talk about this morning is regarding our research is to look at dynamical downscaling, where we run a mesoscale model at higher resolution to look at the processes associated with the water cycle. So we're looking at the physics of the processes. And the example I'm going to show, which is of high interest to us in the United States, is Colorado Rockies, located right here by this X. And the global model shows an increase of precipitation of 3%, soil moisture decrease of 6%, evaporation about plus 6%. and we have a decrease in runoff of minus 12%. This is of great interest because much of the water for the whole western United States and Los Angeles, Arizona, comes from the snowmelt from the Colorado Rockies right here. So if we're going to get minus 12% decrease, then we have to take action. This is a large societal impact. In fact, many previous scientists have suggested potentially up to 50% decrease in runoff in this region. So what do the models say in terms of the global average temperature anomaly? As I showed you, most of them agree there's going to be warming. They also suggest precipitation increase, but with a large amount of variability. This is going from 1950 to 2100. And because of this large variability in precipitation, if you look at the runoff from the models, you see a large variability from this period 1950 to 2100. This is the average, sort of the 5% increase, but a large amount of variability. So again, the water cycle is really not handled all that well, even in today's global climate models. So what I'm going to talk about in the rest of this talk is to look at the research that we've been doing in Colorado, looking at a snowmelt-dominated region, basically here. But the type of research we're doing can apply to other locations, such as Thailand. So it's a so-called pseudo-global warming approach that I'm going to talk about. It was developed by some Japanese scientists and Chris Shar in Switzerland. And we try to answer two basic questions. Does the predicted increase of precipitation offset the expected increase of evapotranspiration over complex terrain or in a warmer climate? So Thailand does have complex terrain, especially to the north, and that's where a lot of your precipitation occurs as well. And then how does this impact the future runoff? This is what a lot of water resource managers are very interested in. And as I said, I'm going to focus on Colorado, but this could be anywhere in the world, as you'll see. So I'm going to talk about a high-res simulation, and then talk about a climate change simulation using a pseudo-global warming, and then do a budget analysis at the end. And again, I mentioned my team. There's a lot of different aspects of running these kind of models, from the model setup to running the model, to analyzing the data. We also have a snow physics part of this as well. We've looked at statistical versus downscaling, dynamical downscaling, and I have a list of papers at the end of my talk if you're interested to learn more. So what's the problem we have in Colorado, in the North America? Well, in January 2002, this is a MODIS satellite image of North America, and you can see all the white is snow cover, and our region of interest right here, Colorado Rockies, Colorado headwaters, is in this red box. So what happens in March? You can see there's a little bit of change, but by April we have tremendous melting. So the melt season is really March, April, May, and this is when all the snowpack runs off. So you can think of the snowpack as a reservoir of water that all comes out. Like they open up the reservoir in March and April, and that's what's key about it. It's this temperature driven, so you can imagine that climate change could have a big effect. And this is just some pictures of the snow in Colorado and the Rockies. You can see a lot of it's on the peaks, and then you have a melt level at a certain level down. Some of it's on a flat mountain. This is the Grand Mesa in Colorado, very flat. But again, it's a great reservoir. You can almost imagine this as a reservoir like this, all this water. Then it warms up in the spring, and then it all melts and comes down into the rivers, Colorado River. This is where I live in Boulder, Colorado. So you can see all the snow on the peaks. In the spring it melts, comes down the rivers, and then it's used for irrigation of the crops. I think this is wheat. So just to get you oriented then, why is this important? Well, because this is a map of Colorado, and these are all different river basins, and they feed different rivers. For instance, the Colorado River is one of the most important rivers in the western U.S., has its headwaters right here in Colorado. The Gunnison, the San Juan, the Rio Grande, all of these major river basins major rivers have their source region in these Rocky Mountains. So water resource managers are obviously very interested in what's going to happen there. So what we did is we decided to do first of all, to make sure the model works right, we decided to do a high-resolution simulation over this region. So here's Colorado, the domain I just showed you. And this is what I call a subdomain, or I'm going to call this headwaters domain here in the rest of my talk. And the brown is the high elevation. This is a terrain elevation in meters, so 3,000 to almost 4,000 meters in some locations. You can see it's quite complex terrain. And now if you look under zoom in, you can see these white areas are almost up to 4,000 meters. Now these black dots are very important. Those are the observation points. So luckily we have over 113 snowtell sites where we have snow gauges, where we measure the snowfall amount, and we measure the snowpack. So these are very useful because we can verify our model runs using these data. This is really a great thing. If you want to learn more about what I'm going to talk about today, in the background there's a paper in Journal of Climate, came out in 2011. You can take a look at that. So what do these snowtell sites look like? Well, this is a picture of one. It's got the long tube. The snow falls into the tube and it's measured. Why is it so tall? Well, guess what? The snow can go up this high. So we have lots of snow in the mountains in Colorado. Again, big reservoir of snow. And there's also something called a snow pillow on the ground, and this measures the weight of the snowpack. So this 25-foot snow or the 3 or 4 meter snow, we can measure the weight, and this measures the snow falling from the sky. So I can use that data to verify my model runs. So this is the way we set up the model. So we use the Weather Research and Forecast model from NCAR, version 3.1, for those of you who like to use WRF. And we run a single domain. This is probably the most important part of this. And it's 45 levels, and we have a 4-kilometer grid resolution over this whole domain. So this is very high resolution. Most climate models are running at around 100 kilometers. Even regional models are running 50, maybe 25 kilometers. So this is factors of 10 to 20 higher than the global models. And this is some information. The only thing I want to mention here is that the cloud microphysics scheme is very important. This was a surprise to us, but we found out that this particular scheme, Thompson's scheme, does the best, and it gives us answers within 5% of observations. The way we run this is we run it with 3 hourly, 32-kilometer North American reanalysis data. So the reanalysis data is used on the boundary conditions here, and it's used to drive the model inside. And that's how we do it, and there's no statistical downscaling, but that's for the current simulation. I'm going to look at three different terms. I'm going to look at precipitation, evapotranspiration, and runoff. And all three terms are included in the NOAA land surface model. This is an image showing a water vapor loop. And see if I can get it to work. And this is from the model. And you can see at 4-kilometer resolution, you can capture high amounts of details in terms of the flows and fluxes of water, especially in the atmospheric water. You can see cold air coming down. You can see some flows coming up from the south. All of these weather events are captured when you do the model at 4 kilometers. And we run this for 8 years. And then what we do is we perturb it with a climate perturbation. But before I get there, I want to mention the verification. So we ran the model at 2 different resolutions, 2 kilometers and 36 kilometers. This is over what I call the headwaters domain. Here's the snowtell that I use for verification. So here's the data that we compare our model to. This is the snowfall amount on an annual basis in millimeters, 0 to 1,000 millimeters. So if you look at the patterns, here. Here's some high elevation terrain with some blue